Hello, I am Audit, the assistant professor in Gargi Memorial Institute of Technology at Basic Science Department. So in the last few lectures of the statistical mechanics, we study about what is microstate, what is macrostate, what is phase space, what is phase cell, density of state, and we separated the statistics in a three ways for the different type of particles. So in the today's lecture we consider Maxwell's Boltzmann statistics. Maxwell Boltzmann statistics is also known as or classical statistics. These statistics only responsible for the any type of classical gases, molecules. This whole statistics is obeyed by the any type of gases. So for the starting, try to construct the distribution function of the Maxwell-Boltzmann statistics for the any type of gases. We have two basic postulates. One is called the particle must be spinless. So obviously this is a gas particle. This particle does not have a spin. Distinguishable. Now you have to say me that how it is possible that each molecules of a gas have a same characteristic. How you consider as a distinguishable particle? That because suppose think that in a classroom, you just enter in your classroom, you have a 20 seat, but you occupy the one seat. So suppose you just occupy the first row, first sheet of the classes. So I'm the observer. I can observe you that you just occupy the first seat. So that's why you can distinguish from the others, because suppose there is a 80 chair in a classroom, you just occupy the first row, first chair. Okay, so that's why I can if I am an observer, I can easily observe you as this molecule. You are a molecule, you occupy the first chair. I can observe that this molecule occupy the first chair. So this is distinguished from the any other particle or any other students in a class. That's why the particle is distinguishable. Second, not follow the Heisenberg's uncertainty relation. Obviously this is a gas particle, this is a classical state, this is not a constant. The Heisenberg uncertainty principle only applicable in a quantum state. And the third one is exclusion principle of Pauli is not applied. What is said by the Pauli? Pauli said that the same value of what is Pauli exclusion principle? Pauli exclusion principle says that same value of spin cannot be occupied by the one energy state. That means if electron can occupy the one state, if two electron can be occupied with the one energy state or one energy value, the must be the two electron have a two different value, different with a different spin. This is said by the Pauli in a Pauli exclusion principle. Now we try to construct the distribution function for the Maxwell Boltzmann statistics to consider this basic postulates. If let total number of particle is n is considered as a ni is equal to constant. For in a gas chamber, obviously number of particle will be constant, so that means ni so we can rewrite that del ni equal to 0. What is say that? Conservation of number of particle. Is it clear? Also, the total energy is U Ni Ei equal to constant. What is Ni? Ni is the number of particle, E is the corresponding energy state. So that means summation over Ni Ei is considered as N1 E1 plus N2 E2 plus N3 E3 dot 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 dot. That means first particle is with the first electron have an energy of E1, the second electron N2 number of electron N2 have a energy E2, the so total energy is Ni into Ei, because total number of molecules into respective energy. So this is the total energy. So from this one we can consider as a del Ui is also 0. Conservation of energy. Is it clear? So first of all we consider the total number is constant in the system and total energy of the system will be constant. Now we try to consider a new page. Let n be the total number of particle is assembly by n1 n2 n3 and so on. Now that we try to find out the distribution function of this such type of particle. The number of ways in which the group of particles n1 n2 n3 dot 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 last ni could be occupied. The total for the total particle of ni, the total number of state is n. Okay, suppose you are enter in a classroom, you have a 20 seat. Okay, you have a possibility of choosing the 20 seat in a total classroom. So the possibility is 20. So n total n is considered as a 20. How many possibility you have? 20. You just occupy you have the probability of 20 by u. Okay, then your friend 1 is considered. You just occupy the one seat. You just occupy the one seat. Okay. So how many particles, how many cities remain? So Ni is not now 20. It is become 90. So N2. The occupation of the particle is N2. Next one is come N3 dot 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 Ni. Is it clear? The total occupation is 20, but when you enter, you have the probability of 20. When your friend is entered, their probability is 90. When next one enter, the probability is become 18. When the next one enter, is probability become 70. So every probability is become decreasing. This is the total probability. When you enter, N1 is 20. When, because you occupy the one seat, now the total seat is unoccupied is 19. When N2 enter, the occupation rate of the N2 is probability is 19. So N2. N3 is equal to 18. Is it clear? This is the number of way the particle can be occupy the energy state. Okay, the first particle occupy the energy state. And clear. So the again the number of ways in which Ni particles could be distributed in GI state. Suppose this is occupied by the particle. Suppose you have a GI state. You have a in a microstate macrostate chapter lecture, we have considered that there is a 3 particle is occupied by the 2 boxes, or 2 particle is occupied by the 3 boxes. Suppose you have a GI number of boxes. Okay, and you have a obviously in with Ni particle, then the distribution function must be Gi to the power Ni. Is it clear? It is you remember by that the number of state whole to the power number of particle. This is the microstate distribution of any particle, because you have a Gi number of boxes you occupy by the Ni particle. So distribution function for the microstate is Gi to the power Ni. So it is written by G1 to the power N1 into G2 to the power N2, G3 to the power N3 dot 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 Gi to the power Gn to the power Nn, written by N, I tends to 0, Gi to the power Ni, the total 1, written by W2. This is the productive summation function. Everyone is, it is considered EI is considered as E1, E plus, E2 plus E3. So this one is considered as E1 into E2. Clear? So now the total, the distribution among the state is written by W into W1 into W2. N summation over ni factorial summation over gi whole to the power ni. This is coming from here, n factorial divided by ni factorial. Clear? So this is coming, w1 is responsible for the occupation of the particle by the each state, and this portion is, this is by the particle occupied by the each state, and this is responsible for the microstate distribution. This is the whole distribution function of state. Consider as a equation 1. Now take logarithm in both side. So become ln w is equal to ln n factorial plus ln gi to the power ni minus ln ni whole factorial, because this numerator term is become negative and the numerator term is become positive. Logarithm formula. A new thing we taken here, just consider ni ln ni plus ni. We separated this function in terms of this full one and this one in this full one. This is a string formula. String formula says that ln ni is equal to n ln n minus n. Is it clear? So del ln of n factorial is written as n ln n minus n, and similarly ln of ni factorial is written as summation over ni ln ni minus summation over minus li ni ln ni minus ni. We have I have considered this string theorem in here. Okay, n ln n minus n plus ni ln gi minus ni ln ni plus n, because summation over ni is equal to n. Cancel out this one. N ln n plus ni ln gi minus ni ln ni. Is it clear? ln w. Now for the most probable distribution, the entropy S is written as a k ln w, where is the k is a Boltzmann constant, S is entropy of the system. Entropy is a one type of thermodynamical function, is written by a k ln w. K is a Boltzmann constant and w is the distribution function. That's why we chosen here. We are evaluated w in term of ln w, and also we have Ni equal to 0. Del U total energy Ui del Ni is also 0. This is the conservation of total particle. This is the conservation of energy. So now from equation 1 and 2. So now from this equation 1, 2 and 3. Clear? For maximum of W, ln, we have ln W is equal to n ln n plus ni ln gi plus ni ln ni. From equation 1 we have ln W is equal to n ln n plus ni ln gi minus ln ni. We're taking the differentiation in both sides. Ln W is equal to, this is the total number of electron, obviously the differentiation is become 0 plus ln gi minus ln ni del ni equal to 0. So 0 is equal to ln gi minus ln ni del ni, because we consider for the maximum value of W, del ln W is always be 0. Now by the Lagrangian method of undermined multipliers alpha and beta. Equation 4. This one is equation 4. Minus alpha and minus beta multiply with equation 2 and equation 3. Okay, equation 2 and equation 3, and add with equation 4. Clear? So this is the equation 4. So equation 4 is considered as a summation over ln gi minus ln ni. This is the equation 4. So alpha is multiplied respectively of minus alpha is multiplied with equation 2. What is equation 2? Equation 2 is del ni equal to 0. So minus alpha del ni plus minus alpha del ni minus beta. Beta is also multiplied with equation 3 ei del ni ei del ni equal to 0. Clear? This is the equation 4 is added with equation 2 with multiply by alpha, and equation 3 is added with the equation 4 with multiply by minus beta. So this one is become ln gi minus ln ni minus alpha minus beta ei del ni summation. So L G I minus L N I minus alpha minus beta E I equal to 0, where del Ni not equal to 0, it is independent. Ln Ni is equal to ln Gi minus alpha minus beta Ei. So I have ln Ni is equal to ln Gi minus alpha minus beta Ei, or ln Ni is equal to ln Gi minus ln e to the power minus alpha minus beta Ei. We can rewrite this minus alpha minus beta Ei in term of ln Ei alpha exponential to the power minus alpha minus beta Ei. So it is become ln Ni ln Gi into e to the power minus alpha minus beta Ei using the logarithm formula. So it is become Ni is equal to Gi e to the power minus alpha minus beta Ei, or Ni by Gi is equal to e to the power minus alpha minus beta Ei. Fei is equal to e to the power minus alpha minus beta Ei, where Fei is equal to Ni by Gi. So this is called the distribution function of the system. So this is the distribution function of the system. It derived from the consider the some basic postulate. Heisenberg unsearchable cannot be considered. Pauli exclusion principle cannot be considered. The particle must be indistinguishable and identical. And the total number of particles in the system will be always be constant. Total number of particles is always be constant. Then we choose. Then we consider the particle can occupy the each cell by itself. This is the occupation by the particle, and this is the total number of microstate of the system. So total distribution function of the total particle and the total microstate equal to, then we take the logarithm on the to both sides. Then we using the string theorem. I have a brief note on the string theorem in the next lecture. Okay, now today's lecture you have just considered that n factorial always be equal to n into ln n minus n. So n factorial, similarly things happen here, ln n ni factorial. So summation over ni ln ni minus ni. Okay, so total ni is cancelled out. Then we consider the entropy of the system. For the in a equilibrium, the entropy of the system always be 0. In a equilibrium, the entropy of the system always be zero in a equilibrium. So that's why S is equal to, we know the equation from the entropy with the distribution function is S is equal to K into ln W. So when the S is become 0, obviously ln W is also become 0. So we consider this, when we calculate the ln W in term of Ni and Gi, we consider. So this is ln W is equal to 0 del. So then we get this equation. Then we multiply the equation 4 and equation 2 and equation 3 with the two arbitrary constant alpha and beta. Next we try to evaluate that what is alpha and what is beta. Then multiply with the equation 2 and added with the equation 4, equation 3 and added with the equation 4. Then just simplify this equation, we get the Ni by Gi and get the exponential over minus alpha minus beta Ei. This is the total distribution function. Next day we have to try to construct the distribution function for the Bose-Einstein statistics for the boson particles and also try to evaluate the value of the alpha and beta. Thank you.